Okay, let's begin. Someone came up to me after the last one and they said they tried this code and something went wrong, and we figured out why. So in all of my slides, if I have a bit of Python code, I'm using Python 3. And one of the changes between Python 2 and Python 3 was that if you have an integer over an integer, in Python 2 you would get an integer, and in Python 3 you get a floating point number. And so when I was doing this normalization, you were getting some kind of funny results, and the probabilities were coming out as being integers, which were all 0. So this assumes Python 3, just FYI. So there are huge numbers of families of probability distributions, and they all have their uses, but these are some of the popular ones. In astronomy, there aren't that many discrete distributions that are used a lot, although there are probably some that should be used in certain situations. I'm sure Ewan will have some things to say about that in his lectures. But some basic ones: discrete uniform, binomial, and Poisson, we looked at just briefly. So here's an idea for when a discrete uniform distribution might be useful in an astronomy application. If you have a spectrum and you think there's a bunch of emission lines in the spectrum, but you don't know how many there are, one way of modeling the fact that you don't know how many there are might be to have a uniform distribution between 0 and 100 over the integers. So you can't have fractional numbers, so you would just have it for the integers. The binomial distribution, here's an example where it might appear in astronomy. So this is to do with the number of things, the way we usually talk about it is the number of successes out of n trials of something with a fixed or a constant success probability on each trial. And here's just a little astronomy story I made up about the binomial distribution. So suppose 30% of stars have a certain kind of oscillation signal if you observe their variations, and you take a sample of 100 stars and you're interested in how many of those 100 stars have this oscillation. And then the distribution for that number, if I call that number x, is a binomial distribution. And I've written this down here with this notation, which is a very common notation, certainly among statisticians, for quickly writing down the probability distribution of something. So if I wanted to tell you that x has a binomial distribution with these two values of its parameters, 100 trials and success probability of 0.3, those are the two numbers that say which binomial distribution I'm talking about. Then this is one way of writing it. I write the name of my random variable, and then this tilde, which I called twiddle, based on well, I had a stats professor in first year undergrad, and he called it twiddle, so it's good enough for me. So if you write x, twiddle's binomial, and then how many trials, and what's the success probability, that's a very concise way of saying what the distribution is, and you don't have to write out the formula for the probability distribution at all. So I'll be using this notation throughout to write down assumptions about distributions. So this distribution, if you were to look at it, it would be a distribution over the integers from 0 to 100, because if there are 100 stars, then the number that have the oscillation could be 0 or 1 or 2 or 3 or 4 or ... up to 100. So there's 0 probability for anything other than those integers. And it would probably peak at somewhere around 30. I haven't plotted it exactly, but you can imagine some distribution centered somewhere around 30 with some kind of a bell curve E shape, if you were to plot that distribution. Also, I said here in this little note, this is again my little obsession, is that this assumption in the sentence is that there's a certain frequency of a population that has a certain property, and I just assumed that the probability that stars in my sample would have that property is equal to the frequency with which stars in general have that property. And that's an assumption. I'm equating two concepts. I'm just giving them equal values, even though the concept of what proportion of stars have this property is a completely different concept. It could in principle be completely different from how certain I am that a particular star has that property. So I'm just trying to completely separate the concepts, even though it often makes sense to set the values to equal each other. The Poisson distribution is probably the most popular discrete distribution that arises in astronomy because it has applications like the one here. So if you know the intensity of an X-ray source, so the kind of typical number of photons that would come in any time interval, and you care about the actual number of photons that appear in a given time interval, then the Poisson distribution is what you'll want to use. And so if you would expect to detect lambda photons per minute, so you know the intensity, you know that that's the kind of long-term time average maybe, and here I'm going to equate a long-term time average with just a quantity in the Poisson distribution, which is a very common assumption. If x is the number of photons, then the distribution of x is Poisson, and the Poisson distribution is a family of distributions that has one parameter to say which Poisson distribution I'm talking about, and it's the one with parameter lambda. And these different families of distributions have different numbers of parameters, and the parameters usually have meanings that are specific to that family of distributions. So with the binomial, if it's written in general without specific numbers here, it's usually written as binomial n comma p. So n's the number of trials and p is the success probability. Poisson is usually written as Poisson lambda, and the meaning of lambda is that it's the expected rate of arrivals, and it also turns out that lambda is the expected value of x. And in this one, this times that is the expected value of x. Okay, so each family of distributions has its own parameters with their own specific meanings, and actually Wikipedia is amazingly good for information about probability distributions. So if you just go Poisson distribution, you'll find like 10 times more information than you need about it. And that's true of almost all the distributions that have names. So I've written it in this twiddles notation as well. I've said that x twiddles Poisson with lambda, but there's an extension to that notation that I'm assuming that this lambda is known and that this is the distribution that x would have if I know lambda. It's because it's got lambda on the right-hand side. So to use a Poisson distribution, I have to know the lambda. So this is also, this extra notation is to just say that this distribution is a distribution for x given lambda, and I have to put that there because lambda appears on the right-hand side. Sometimes people write it without the given lambda, and just that's understood to be implicit because lambda appears on the right-hand side. I just thought I'd show you the kind of full notation that you see. The equation for the distribution is this. So I'm using here the simple notation, and that's the formula for it. And what it looks like is something like one of these three densities, one of these three distributions. These are three Poisson distributions with different values of lambda. And remember, lambda sets the expected value of x in this case. So if you have lambda being 3, then you'll get the blue distribution where values around 3 are very probable. If lambda's 6, then you have this orange distribution. And if lambda's 15, you have this green distribution with centered around 15 and with expected value 15. So the Poisson distribution has two properties that are useful and worth remembering. One is the sample space, and you can infer the sample space from the story. So if the story is about how many photons will arrive. So it could be none or 1 or 2. It's a count, and the Poisson distribution is often used for something that is a count. So that's the sample space, and this parameter also has a restriction. It must be non-negative, but it needn't be an integer. So lambda is non-negative real number, and x is a non-negative integer. Okay. So that's what Poisson distributions look like and what they're often used for. In astronomy, it's more often that you'll see continuous distributions used for things, and continuous distributions are a generalization to the case where the hypothesis space is a continuous space. So something like all real numbers, or all real numbers between 0 and 1. Things like that. So the way those are described is that instead of having a definite probability for every specific value, and all those probabilities add up to 1, you can't do that anymore because the number of possibilities is infinite, so you would have a 0 probability for everything. Instead, what you have is what's called a probability density function, or a PDF, which is some function that doesn't give you the probability of each specific value, but it's a function that you can integrate over any region, and that integral gives you the value of the probability of being in that region. So if I say that x can be any real number, and I assign a probability distribution to describe my uncertainty, the probability that x equals any specific value is going to be 0, because equaling a specific value is kind of an infinitely specific statement. But you can get the probability that it's in any interval by doing the integral of the density function over that interval. Okay. So here, a very common example of a continuous distribution that pops up all the time is the normal distribution, or Gaussian. And here is 2 ways of writing down the assumption that x has a Gaussian distribution, or a normal distribution. I've got here this same notation with the twiddles, x twiddles normal. Normal distributions have 2 parameters. There's the mean parameter, which is the first one, the mu, and that just determines where it's centered. And sigma, which determines the width. And sigma is the standard deviation, and sigma squared is the variance. And the way statisticians usually write it is they write it as mu, comma, so mean, comma, variance. But because it's easier to think of variance in terms of standard deviation, because it's in the right units, standard deviation having the same units as x, so we write down mean, comma, variance, but the way we write the variance is as the standard deviation squared. So I've got here sigma squared. So if I wanted to have a normal distribution, looks like a bell curve with mean, with standard deviation 2, the way I would write it down is normal, some mean, comma, 2 squared. Because you're supposed to write the variance in there, but I want to be able to look at the standard deviation without taking square roots. So you write it as 2 squared. So in general, sigma squared. And again, because this normal distribution depends on these 2 parameters, this is really the distribution for x conditional on those 2 parameters. So you can write that on the left-hand side. And here's the equation for the probability density function. If you do this a lot, you'll get used to this formula. Otherwise, you can look it up. But you've got something like e to the minus a half x squared, and then the mu just shifts it, and the sigma just flattens it out or concentrates it. The square root 2 pi out the front is just for normalization purposes, so that the whole integral of that is 1, which is the normalization property in the continuous case. So this is the kind of full notation that you'll see in statistics stuff, where big X is the random variable, little x is a dummy variable, and the equation for the density function is written as f subscript big X as a function of little x. And don't know how to fix this, but for some reason, when you use Beamer, it uses this font where little x looks like a big X, so, but smaller instead of being a curly x. So if someone knows how to get curly maths in Beamer, I would like to learn that. Okay, so that's the kind of full notation. You've got the big X and the little x. It's annoying in the same ways as big P of big X equals little x is annoying. So a lot of the time we just ignore that and just write little f of little x and rename big X to little x as well. Or you can write P. So you can write P just like in the discrete case, and then you still just read it as the probability distribution of x, but you just have in the back of your mind, you know that x is continuous or discrete based on the context that you're working in. Or if you want to emphasize the difference between the discrete things in your problem and the continuous things in your problem, you could use little p for the discrete things and little f for the continuous things. So you'd have like the discrete probability distribution of y maybe times the continuous probability density function of x given y, say. So just as with continuous distributions, we have all these properties of discrete ones, and you can define them the same. You just take everything that was in the discrete case that had a sum, and you just take out the sums and put in integrals instead. And these integrals are implicitly all over the whole sample space or the whole set of possible values of the random variable. So you've got the normalization condition, which is that the integral of the density function over the whole range needs to be 1. That's equivalent to the sum of the probabilities being 1. The expected value has the same notation here, and it's just an integral of x times the density. And the variance has the same definition, and it's got the expectation here, and it's just an integral instead of a sum, and the standard deviation is still the square root of the variance. So very easy to interchange the sums and integrals. And if you just remember things one way in terms of sums or integrals, then you know them the other way as well. And again, these have the same meanings as they did before. So the expected value is the center of the distribution, and the standard deviation is the width, or one way of formalizing those notions. And I mentioned this before, but for normal distributions, the two parameters are the mean and the standard deviation squared. So mu is the expected value. So if you chuck an x in front of here and then integrate it over the whole real line and then do some maths, you would get mu and sigma as the standard deviation. Okay. So as with discrete distributions, to handle them in one dimension is quite easy to do using numerical software packages. So here I've just got some NumPy, mostly NumPy stuff again. And might be hard to see. Is it hard to see? Sorry about that. Hopefully you've all got a copy anyway. I'll just go through and point out any differences between this and the discrete case. So the first difference is that I'm using a linspace to make a grid of possibilities instead of using a range to make an set of integers. Here I'm making a set of floating points, and it's finite because you can't have a continuum in a computer. So I've just made a sample space that goes from -10 to 10 in steps of 0.01. But the understanding is that this is a discrete approximation to a continuous case, and that really I should be using as fine a grid as I can within computational resources, and hoping that my grid is fine enough that none of the answers are sensitive to how fine I made the grid. So I'm just using a linspace to define the possible values of x, the x's. And here I'm just making a normal density. I'm doing it in 2 steps. I'm just making p's equals the x part of this formula, and then instead of putting the normalization constant in front, I'm going to normalize it numerically instead of using the formula. So I've got e to the -1/2, the x is -2 over 1.5 all squared. So recognizing that as a normal distribution with a mean of 2, so centered at 2, and with a standard deviation of 1.5. So this would model the case where you have some prior information, perhaps from a previous data set, that indicated that x was somewhere around 2 plus or minus 1.5. If you want to model that and use a normal distribution to do it, then this could be how you set up your prior distribution. We'll come to that in the next section. Here I'm just normalizing it numerically, just making it sum to 1 by dividing by whatever it happens to already sum to. But instead of a summation, it's an integration, and I'm just using the trapezoidal rule. So I'm using traps of the p's, and the x value for my trapezoidal rule is given by the x's, and that's just the equivalent of an integral. And you can plot the density, and you'll get just a nice bell curve centered at 2, standard deviation 1.5. Expected value and variance, they're the same. We just, instead of using sum, we're using trapezoidal rule to approximate the integral. So trapezoidal rule, integrate the x's times the p's, and the p's are not probabilities, they're densities, and the x values for the trapezoidal rule are the x's, and similarly for the variance. and also for the probability that x is greater than or equal to 5, which I've got in this example. Actually, there's a slight complication. In the previous example, I had np.sum of a subset of the p's where x was greater than something, because I wanted to just add a subset of the probabilities from the distribution. Here, there would be a bit of an awkwardness if I tried to do the same thing. If I tried to do p's and then take the subset with square brackets where the x's are greater than or equal to 5, then the trapezoidal rule would complain because I would have a subset of the p's which would have some length, and I would have the x's and I'd have the full length of that vector, which is annoying. I would have two vectors of different lengths, and it would be trying to do the trapezoidal rule with it, and it would complain. By the way, a mathematician came up to me in the break and said, by vectors, I don't mean vector space vectors, I mean computer vectors or arrays. So I don't think I'm going to have any vector space vectors in any of my materials. So I always just mean arrays. So here we've got, instead of doing the subset, I'm just multiplying by this logical array here, or this Boolean array, where I've got the x's being greater than or equal to 5. So that comparison will give me trues and falses. And if you multiply floats by trues and falses, it just sets the falses to 0, because the falses are like zeros and the trues are like 1. So instead of integrating over, so I'm integrating over the full space, but I've set the stuff outside the region that I care about to 0 before doing the integral, which is equivalent. Okay. So in one dimension, if you have one unknown parameter or one unknown thing, random variable, say, then it's very easy to do things numerically. If you have multiple unknown parameters or higher dimensional situations, then these techniques start either becoming obnoxiously complicated or even computationally infeasible, and that's what Monte Carlo methods are for, to overcome that, and we'll be looking at that after lunch. So there's lots of continuous distributions. They seem more useful than discrete distributions in the physical sciences, I would say. Here are some distribution, and this is just like the discrete uniform, except it's continuous. So when I said that you could have a uniform distribution from 0 to 1, and it could be any real number between 0 and 1, that would make it a density instead of a discrete distribution. Normal distribution we just looked at is very commonly used to model the distribution of the noise that you would expect to see in your data. And I just said a sentence. I'm very nitpicky about these sentences that I say. So I said, the normal distribution is often used to model the distribution of the noise that you get in data. And what it really is, I would say, is that the normal distribution is often used as your prior for the value that the noise takes in your data set. And if you have noise with if you have data set with a lot of values in it, and you use a normal distribution for each of the values of the noise in your data set, the joint prior distribution for your noise vector, or your set of noise values, is a product of a bunch of normal distributions, one for each quantity. And that's a different assumption from saying that if I took a histogram of my noise values, it would look like a normal distribution. Those two things seem like the same assumption, but they are not the same thing. Okay. Another distribution that I'd like to mention is T. It's called student T distribution sometimes. And it's like a normal distribution, but it's got one extra parameter which controls the shape. So it lets you do things like have heavier tails than a normal distribution. So I think T's are great. I use them a lot. And I think they're underrated. I think people should use them more for this reason. So a normal distribution might look something like that. And one of the properties of a normal distribution is that once you get more than a few standard deviations away from the mean, so if that's the mean and that's the standard deviation, once you start to get 3 or 4 or 5 standard deviations away, the probability in the tails goes down towards 0 really, really fast. And it goes down towards 0 so fast that you're basically assuming there's no chance that the value is more than a few standard deviations away. Whereas t-distributions, depending on the value of that third extra parameter, so they'll have something like mu and sigma, but they have this third parameter, which is often denoted as nu, which is called either the shape parameter or degrees of freedom. And again, you can just look it up on Wikipedia. It basically controls how much fatter the tails are than a normal distribution. So if I have a t-distribution with this thing set to 100, you pretty much get a normal distribution. So it kind of reduces to a normal distribution in a certain limit. So that's my attempt at drawing a label, that the dotted line is with a t-distribution with a high value of this third parameter. But if you have a low value, then what you get is that it still kind of has a width of sigma. It's not that the standard deviation is sigma, but it's still a measure of width. But you have a lot fatter tails. So the way it goes to 0 is a lot gentler as you get far away from mu. So that would be something like if you had nu of 1. And I think the restriction on this nu value for t-distributions is that it has to be greater than 0. So I mentioned that you might use a normal distribution if you had a previous data set or a hunch or whatever, that you had some previous estimate of your parameter and some uncertainty. So maybe it's 5 plus or minus 1. You might assign a normal distribution to model that. But you need to think about, are you really sure that it's very unlikely to be more than a couple of standard deviations away? So if you say 5 plus or minus 1, does that really mean that you've basically ruled out that it's greater than 10? If you haven't, if you want to take into account that assumption but make it more forgiving of the fact that you might be wrong, t-distributions are a great way to do it. There are gamma distributions. These come up from time to time. They have nice mathematical properties. They work well with other distributions. I'm not really going to go into that. Something called conjugate priors, if you want to look it up. That's a 2-parameter family of distributions for positive random variables. And with the t-distribution, I'll just draw a sketch of the kind of thing you can have. Sorry, with a gamma. So t's look like this. Gammas, depending on the values of the 2 parameters, you can have things that look kind of like normals, and you can have things that look kind of like that. And by varying the 2 parameters, you can control how far, basically where the distribution is centered and how wide it is and things like that. You can get kind of shapes like that. That one doesn't really look like a gamma, but I apologize. But this is the kind of thing that comes into mind. When people say a gamma, it's probably a thing like that. And astronomers, I think, have reinvented gamma distributions under the name Schechter functions in some context, and someone can correct me if I'm wrong about that. Am I wrong about that? Am I right about that? Does anyone know? No one knows. Okay. Exponential distributions are useful as well. So those are things that look like e to the minus x. So you'll have a density function that decays exponentially. Those have 1 parameter. And one good use for exponential distributions is in a situation like this one where I had a Poisson distribution. This situation, I had a Poisson distribution if I asked the question, how many photons will I see in this particular interval? But if I ask a different question about the same situation, if I ask, how long will it be between one photon and the next? That has an exponential distribution. So the same set of assumptions, it's called a Poisson process. You can look that up if you do this kind of application a lot. A Poisson process is a model for a bunch of things arriving in time, and its main 2 properties are that if you say how many arrivals happen in this time interval, you get a Poisson distribution. And if you say, how big are the gaps from one arrival to the next, you get an exponential distribution. And actually, it has more properties, like if you say, how long is the time interval from the 5th photon to the 7th photon, so the gap between two non-consecutive photons, then you would get a gamma distribution. There's all kinds of nice properties of Poisson processes, and I'd recommend reading about them if that's the kind of application you work with a lot. Another thing that astronomers do a lot is they use power law distributions, and the statistician's name for those is Pareto distributions. And yeah, those are power laws. So if the density function is something like, so you've got some lower limit for below which your quantity can't go, and the density function is something like x to the minus a power in shape as you go out from that lower limit, then you have a Pareto distribution. And I have an example at the very end of the day, if we get to that, where I use a Pareto distribution. And the way I infer the parameters of it is not what astronomers usually do. So to infer the parameters of a Pareto distribution, you'll often see papers where people plot a kind of empirical cumulative distribution. So say you measured the mass of a bunch of galaxies and you plotted the number that have a mass greater than something, and you put log axes, I think it's log on both axes, I might be wrong about that, then you would expect to see something like a straight line, and then the slope of that straight line gives you one of the parameters of a Pareto distribution. And that kind of works, especially if you have a large sample size. Usually if you have a large sample size, kind of anything non-crazy will work. But if you have a smaller sample size and you want to do things more properly, then you should do it using Bayesian inference, using a Pareto distribution. And I would bet, though I haven't checked this, I would bet that this is the case where the difference between doing things properly and doing things not properly actually matters. In some cases, it doesn't really matter. So here are some examples of when you might use these distributions in astronomy. Uniform distributions. So say you have an image and you think there's an object somewhere in the image, you might assign a uniform distribution for the x-coordinate of its position and the y-coordinate of its position, just to say, I don't know where it is in this image, but I'm treating regions as equivalent. So small region means smaller probability, large region means larger probability, and there's translational invariance and all that. The normal distribution is very common for noise in data. How much will my measurement depart from the true value of the thing I'm measuring because of whatever observational effects are? The normal distribution is often used for that. I think it's probably a good assumption to, anytime you're tempted to use a normal distribution, it might be worth trying your analysis with a t distribution instead. It's got those heavier tails, and it can be fail-safe. Because one of the properties that happens with normal distributions, if you're doing, say, a linear regression or fitting a straight line, and you have an outlier or two, the normal distribution will cause the inference to believe the outlier and move the lines all the way over towards the outliers. Whereas if you allow your distribution to be t instead, then it may not do that. So just at the last thing I'm going to talk about in this section before we do some more questions is what probability distributions look like in higher dimensions. And usually we're going to use continuous distributions in higher dimensions. So suppose you had two unknown quantities or two random variables, x and y. Then the hypothesis space, what's the value of the pair x and y, is something like, it's a two-dimensional plane. So it's r squared. Okay. And to have a joint distribution on that space, you will need to assign a function of two variables to be the probability density function, so the joint density for x and y. And that will just be something like a function of 2 dimensions that you could plot with contours or as a surface that tells you what regions are more likely than other regions for the value of the pair x, y. And a version of the product rule applies. So one of the cool things about probability theory is that all the rules that you learn in terms of probabilities of statements, like the basic stuff we did earlier, have exactly the same form when you come to distributions of random variables. And so this looks exactly like the product rule that we had before. Before we had the probability of x and y both being true was the probability of x times the probability of y given x. In that case, x and y were statements, and the big P's were probabilities. Whereas here we've got exactly the same equation for the product rule, but x and y are random variables, and little p of x and y is a 2-dimensional density function, and this is a 1-dimensional density function, and this is a set of 1-dimensional density functions. So these are density functions over the x parameter space. This is a density over the y parameter space that's different for each value of x. And the way you could assign such a thing is to think about, so I've got these 2 unknowns, x and y. I've got the product rule that's going to help me write down a joint density by writing down density for x and then a density for y given x. And so what you could do is you could say I've got this pair x and y, but first I'll just think about x. What does my uncertainty about x look like? How wide is it? What shape should it have? Blah, blah, blah. And then you could choose some distribution for this. And that, by the way, is called the marginal distribution for x. So that's the joint. That's the marginal. And this is the conditional distribution for y given x. So you could first write down assumption for x, and then you could say, well, if I knew x, would that tell me something about y? If not, you can just you could say x and y are independent and just write down a distribution for y as well. If they are dependent, so if x would tell you something about y, then your job here is to write down a distribution for y that has x as a parameter of that distribution. And once we start doing examples, hopefully that will become more clear. If you want the probability that x and y are in any region, you just integrate the density function over that region. So I might just draw an example in case it's not entirely clear and write some terminology. I'm used to magnetic ones, but that's not a magnetic one. Okay. All right, suppose I had two random variables, x and y, and I assigned a joint density function, so some function on this space that is probability densities, and I could represent it as contours like that. So that would be the joint density function. And it would have an equation that is something involving x and y. And if I wanted to know the probability that x is greater than 2, then I would do the integral over that region to the right of that line. And if I wanted to know the probability that x and y are in that region, I would integrate over that region. If I integrate over the whole space, I'll get 1. And so this is the joint distribution by the product rule. It's equal to what I have written on the slide. And this p of x that I said you could assign first on your way to deciding what this joint distribution should be, this p of x is called the marginal distribution of x. And it's kind of like if you collapse everything in this plot just down onto the x-axis and look at how probable each value of x is, or how much probability density there is, you'll get a 1-dimensional distribution like that. And that's the marginal distribution of x. And this is the joint distribution of x and y. So joint and marginal distributions come up a lot. Yep.
So I guess this idea of extending to higher dimensions works on any differentiable manifold, not just on a plane.
Yes.
But then, so you could integrate over a sphere, but then
Yes.
you wouldn't have these marginal probabilities, would you? Because you couldn't assign coordinates globally. I mean, how would you?
I think you would. This is beyond my pay grade, but I think if you wanted to, so if you had, let's say, a joint distribution on the sphere,
Yeah.
which is you're perfectly welcome to define such a thing. Could you have a marginal distribution for? Yeah, you could. Yeah. So here's my lame physics way of doing it. You could embed that in 3 dimensions and then put a delta function at the surface, and then you can integrate over that. So but that's putting it in a subspace of R cubed. I don't know. But yeah, this applies over like all sorts of fancy spaces.
Have you ever had to do anything like this? Or?
I have things that I do with where one variable is integer, and as a function of that variable, the dimensionality of the other variables is different. So that's called a transdimensional model. So, but all the probability theory works out exactly the same. It's wonderful. You can just throw caution to the wind and write down the product rule, and I'm pretty sure no matter what the spaces are, it all just works somehow. Okay. It's kind of, I think of this as like a parallelized version of the product rule. So it's kind of, I'm computing something like the probability of a bunch of statements here. Like computationally, you could think of this as a matrix of probabilities equals a vector of probabilities times a matrix or a vector of vectors of what the y distribution would be as a function of x. Anyway.
Okay, thank you.
Yeah. Yeah, I don't know about the super fancy stuff. Okay, so on the board I drew the marginal distribution of x, which is what you would get if you might even get it for free because you may have written down the joint distribution by first writing down a marginal distribution, in which case you get it for free. But there's also a marginal distribution of y, and it's not obvious how you would get that. You could always do the product rule the other way. But then in order to solve for it, you'd have to know that. So that doesn't quite give you what the marginal distribution is for y. But what you can do is what's written on the slide here. This is called marginalisation, and it's a version, comes from the sum rule of probability theory. And one way of seeing that is if I have x and y, and I consider the proposition that x equals 3, then that's the same thing as the proposition that x equals 3 and y equals 0, or x equals 3 and y equals 0.1, or x equals 3 and y equals 0.2. And those are all mutually exclusive, so I can add their probabilities. And so what I'm doing there is I'm taking the joint distribution of x and y and summing over y to give me the probability of any value of x. And the same thing works in continuous situations with the integral. If you take the joint and you integrate over all values of one of the variables, then you get the marginal. And so that's how you would collapse this two-dimensional density just onto the y-axis to get a marginal density of y, which might look like that. What you're kind of doing is that for all values of y, you're integrating over the joint density, adding up all the probability in the x direction and saying that's the density for that y value on its own. And so that's the integral you would have to do. And one of the reasons that Bayesian statistics used to be unpopular, well, there was a kind of a reaction against it by Ronald Fisher, who is the kind of famous geneticist and founder of statistics, really, as a discipline that was distinct from probability theory. A lot of what Why did I start talking about Fisher? I don't know, I just started talking about Fisher. Oh yeah, okay, here we go. So Fisher was very, so Laplace came up with all this stuff centuries ago, or much of it, and then people didn't like the idea of Bayesian probabilities because they're somewhat subjective. You're modeling your uncertainty by mathematical functions, and you have to make some judgment call about how to translate kind of, sometimes even just your feelings into a definite choice of mathematical functions. And Fisher wanted to get rid of that aspect, and you could do that by being a frequentist, but you lose the power of being able to say, you know, the probability of a conclusion. That's what you lose. I've forgotten again why I raised Fisher. Yes. So Fisher kind of won the argument for much of the 20th century, but there were these like underground people, or more underground people, like Harold Jeffreys, who kind of kept doing Bayesian things and thinking it was the right way, and it was very philosophical. But there was kind of a pragmatic argument against doing Bayesian things, was that it has all these bloody integrals in it. Sorry, I'm Australian. And these integrals, unless you make very specific assumptions and work on certain idealized problems, they were hard to do, and you couldn't do them in realistic situations. But the frequentists had an advantage that the calculations they ended up having to do were usually doable analytically, or in more cases. So there was a pragmatic argument against being Bayesian, that you get all these integrals that you can't do. But in about the 1990s, with rediscovery of Markov chain Monte Carlo methods, everyone realized you can do these integrals, or effectively do them computationally by using algorithms that we'll look at soon. And you didn't actually have to be a super powerful mathematician in order to solve problems. So before we get on to the questions for this section, I just want to mention Bayesian and frequentist again. So both kinds of modeling have probability distributions in them. It's the same dichotomy of what's the meaning of the probabilities and the probability densities in the two different cases. So in the Bayesian thing, a probability density or a discrete distribution is something that you write down to model your state of uncertainty about the value of a quantity. And you use it to compute how plausible it is that it's this value versus that value. And the frequentist sense is that these probability density functions are something like histograms. So I use heights of people. If I measured the heights of 1,000 people, made a histogram, then if I wanted to know the proportion of people of a certain range of heights, I would do mathematics that is probability theory in order to do that. And so I've just got an example here. Here is a proposed normal density for the heights of men. And the blue region is the region I want to know the probability of. But the probability is the mathematical thing. But in this application, this is a frequency distribution, something like a histogram of the heights of men in a population. So this is something that's in principle measurable. This describes how many or what fraction of people are of a certain height. And if I want to know the fraction whose height is greater than 1.8 meters out of the subset where the height is between 1.5 and 2, I can do this mathematics. This is Bayes' theorem. And it works out to be the ratio of those two integrals of the function. So that's some mathematics to do a frequentist calculation. So it's just that this function has a certain meaning in the real world. And exactly the same calculation could be used to model the situation where there is one person whose height you care about and you just don't know the height. And this function here is a model of kind of the known unknowns of how you don't, this is the specific way in which you don't know the height. So you don't know it, but you have some idea. You've chosen this function to model it. And you want to know how plausible it is, or would be, for the height to be greater than or equal to 1.8 if you were to learn that it was between 1.5 and 2. And this is Bayes' theorem, and it works out to be that ratio of integrals. So we've got the exact same mathematics, two completely different interpretations of what you're doing, and that's the distinction between frequentism and Bayesianism. Okay. So this is just a bit of an opinion. I think that one issue that I see a lot when I read papers, and I don't know actually if it's a misunderstanding that the person actually has, or if it's just the way we speak, because sometimes someone might write in a certain way, and it doesn't necessarily mean that they actually have a misconception, but sometimes it seems like they do. But one of my pet things to do is I like to be ultra clear when I write down a probability distribution. Am I writing down something like a histogram of a population or a model of my fact that I don't know a single quantity? So those two things have the same maths, and it can lead to confusion if you don't know which is which. Or if you have some kind of mixture of them in the same problem, it can get especially nasty. So there's now another set of questions which we can spend probably 15, 20 minutes doing. These ones are just about some probability distributions, so I'll get you to just fire up IPython or whatever you like, and it's calculations like the ones I had in the slides here. Okay. And I'm going to walk around, and also Michelle and Ewan, the other lecturers that are here, will walk around as well, and feel free to ask questions. And good luck. All right, so I hope you at least got part of the way through one of the questions. If not, again, I'll be around all week if you want to continue working on them. If you did get to the end of question 1, that thing right at the end there, I asked about the probability of exactly 10 photons in 2 consecutive intervals, and so that's the probability that there's 10 photons in the first interval and there's 10 photons in the second interval. And because it's and, you use the product rule to calculate it, and because the non-overlapping intervals are independent, which I gave you in the question, you just multiply the 2 probabilities together, which just means squaring. That's why I've got squared there. So we've got about 15 minutes for me to begin the next section, and then we get to go for lunch and hopefully more coffee. So the first set of slides in the first lecture was on basic probability theory and Bayesian things. So what the idea of Bayesian inference is to quantify uncertainties with probability theory and to update them when you encounter new data and you want to incorporate it. So the way this is usually used in practice is with just a kind of way of arranging things that is called parameter estimation. And it's kind of just a hybrid of the first 2 lectures to make something where you've got Bayesian updating and you've also got probability distributions for things. So in the first set of slides where we were calculating the posterior probabilities of hypotheses, so how probable is it given the data that the person did or didn't have Ebola, was the example. In this section, we'll be calculating posterior distributions of unknown quantities or parameters. And posterior distributions will just be probability distributions like we had in lecture 2. So we'll start with the fact that there's some quantity we'd like to know. Our sample space or our hypothesis space for that unknown quantity is just a set of possible values for it that we're considering, and each of those possible values is a proposition and can be assigned a probability. And when you've assigned a probability to each possible value, you've assigned a distribution, and you've assigned a prior distribution, which models usually a lot of uncertainty. And then when new data comes in that's relevant to the value of that quantity, you update from the prior distribution to the posterior distribution, and you get a different distribution, which models your uncertainty about that quantity, but taking into account the new information. So this is the most common way you'll see Bayesian inference used in astronomy and everywhere else. It's to do parameter estimation, which is just this kind of setup. So I'm going to write down a version of Bayes' rule, but it's not going to be Bayes' rule for the probability of one proposition given another. This will be a kind of probability distribution version of Bayes' rule, like how we had the product rule just at the end of the last lecture. It looked the same as the probability one, but every term in it was a distribution. We're going to have the same thing here. And this version of Bayes' rule is how to get the posterior distribution for some unknown theta given some data d. And so what we're aiming to do is find this posterior distribution, which describes our updated state of uncertainty given the data. And all the terms on the right-hand side are also distributions. So here we've got the prior distribution for theta. This is the thing that describes our uncertainty before taking into account the data. We've got this thing here, which is a little bit subtle with the naming of it. And again, I'm pretty nitpicky on the naming of it. This is a probability distribution for the data given the parameters. So we're going to write down a probability distribution to describe the fact that we don't know the data as well. So this describes the fact that we didn't know the data before we got it. But that there's some connection between the data d and the unknown parameter theta, or parameters theta. These could be collections of quantities. Some connection between the two. Otherwise, learning d wouldn't tell you anything about theta. So we never start from an assumption of independence. If we started from an assumption of independence, then there would be no point doing the Bayesian update because learning the data has nothing to do with the parameters. So it's the fact that we know there's some connection that even enables us to do that. And that connection is expressed through this term, which has a variety of names, none of which I'm entirely happy with. One is likelihood, and that's analogous to the likelihood that we had in question 1. And I think likelihood is good for once you have your exact value of your data, and this is just a function of theta, then likelihood is a good name for it, and that's the traditional statistical meaning. But when you think of it as a probability distribution for what data set you might observe, then that's really not the same thing, because it's not a function of theta, it's a function of theta and d. And one name that you see in the literature is sampling distribution. You can think of it as the distribution which generates the data, although I don't like that interpretation either. Sorry, I'm very picky about what I call things. And what I like to call it when I'm being particularly picky is that it's the conditional prior for the data. So this assumption here that we're going to have to put in any time we're doing a Bayesian thing is a probability distribution for what we think the data would be if we knew the value of our unknown quantities. And so it's a distribution over d that varies as a function of theta. And like in the first lecture, this denominator here is still called the marginal likelihood. So we've got the prior, but it's a distribution instead of a probability. The posterior, but it's a distribution instead of a single probability. Our likelihood, once the actual data is known, this is a function of theta, which modulates the prior distribution. So you get your prior distribution, you multiply it by some function which has to do with the data, and then that turns it into the posterior distribution. There's a multiplication here. And this thing in the denominator is still called the marginal likelihood or the evidence, and it's still, if you think about it, what it is when you don't know the data yet, this is a probability distribution for the data, but not given theta. So it's kind of, what did I know about the data before I got it, but as a single distribution, not as a different distribution for each value of theta. So this is actually the marginal distribution of the data before you got it. Then if the data is actually known, this turns into a single number, which is the probability of getting the data that I actually got. So it's the probability that I would have had before of getting this data, in a slightly funky interpretation. So just to make the connection between the questions you did in part one and the parameter estimation setup, which we're doing now with this prior distribution and posterior distribution and likelihood function, is that when we're doing parameter estimation or just estimating an unknown quantity in a Bayesian way, what we're really doing is considering mutually exclusive and exhaustive propositions, so alternative possibilities for the value of the unknown. So for example, if some unknown theta could be 3.5 or 3.6 or 3.7, then if we assign 3 probabilities to these, then we have a discrete probability distribution. We can have a prior probability distribution. Then if we learn the data and we state the data in terms of a proposition about the value of a quantity, so suppose our data is called D, and then we learn that D equals 5.9, that is also a proposition. And so here we've got 3 propositions whose posterior probabilities we might want to know. One proposition that we didn't used to know was true, but that now we do, we want to update. And we can use Bayes' theorem once for each of these 3 things to get the 3 posterior probabilities. So this is like what we were doing in the first session, but replicated 3 times for the 3 different alternatives. So in the example before, I had 2 alternatives, and we're calculating the probability of something given something else. So this is 3 versions of the original Bayes' theorem that we had. And it actually is, you can think of this as being all within that other version of Bayes' theorem, the one where each term is a distribution instead of a probability. And I've highlighted in different colors what the different parts of those equations are in relation to this version of Bayes' rule. So we're starting with a prior distribution for our unknown theta, which is this distribution. And these red probabilities here, these are just the 3 probabilities not given the data for how likely it is that theta equals 3.5, 3.6, or 3.7. So these 3 values together make up the prior distribution, and those correspond to the little p of theta in the equation on the other slides. So trying to get that whole object, that distribution, in one go. Our blue terms here correspond to this term here, the likelihood function. I'm calling it the likelihood function now because I'm thinking of it as varying as a function of the possible values of theta, but I've plugged in the observed value of the data d. So it's not a function of d and theta anymore. It's just a function of theta. And so what these are the likelihood values like we had in the first session. So if theta was 3.5, with what probability would I have expected to see the data to turn out to be 5.9? Same thing for if theta was 3.6 and if theta was 3.7. So those are the 3 likelihoods. The output of the calculation, what we hope to achieve, is to calculate these green terms, which is just another probability distribution for theta. It's different from the red one, which is the prior distribution. This green one is the posterior distribution. It's usually the thing we want. And it updates our state of knowledge to take into account the fact that we now know that d is equal to 5.9, but we didn't used to. So that's the posterior distribution. That's what we want to calculate. Now we could get this denominator in each of these equations by using the normalization condition. So the fact that these 3 green terms have to sum to 1 tells us that the denominators on the right-hand side, which are all the same thing, has to equal the sum of the products in the numerators. So the probability that d equals 5.9 is equal to probability theta is 3.5 times d equals 5.9 given theta is 3.5. So this denominator equals that product plus that product plus that product. And that's what I meant when I said earlier that I think of this as kind of like a parallelized version of Bayes' theorem. It just looks the same, but everything's a distribution instead of a single probability, and the relationships between all the terms stay the same, and we're kind of doing all this in one equation instead of three. Okay, so that's the correspondence between that slide and that slide. So this is what we have to do Bayesian parameter estimation. And all the examples that we have from now on, I'm pretty sure, have a structure like this. So you can think of it as a function or a machine, and you have to give it inputs, and then you turn the handle and you get certain outputs. And the inputs that you have to give are assumptions about what the unknown quantities are, so what the hypothesis spaces are, choice of the prior distribution, a choice of likelihood or sampling distribution for the data given the parameters. So you have a probability distribution for the parameters, that's the prior, probability distribution for the data given the parameters, that's the likelihood or the sampling distribution. And then you have to give it the actual data as well. Of course, otherwise this wouldn't be data analysis. And then those are the inputs. You do the calculation, and the outputs, you get the posterior distribution, which is a distribution over the same space as your prior distribution, and that describes your updated state of knowledge about the parameters. And the marginal likelihood, which is a single value, which has two uses. One of them is to just normalize the posterior distribution so that it integrates or sums to 1. And the other use of the marginal likelihood is for Bayesian model comparison, which I'll come to a bit later. Okay, how much time have we got? So it's 12 o'clock. Let me see how much I've got for this example. Sorry, 1 o'clock. It's the o'clock that's relevant, so good enough. I think I'll do the example after lunch. I'll go through it. Yep, I'll stop there.